All right, let's talk about calculating volumes by cylindrical shells. So we talked about calculating volumes using the disk/washer method. Um, but another way that we can calculate volumes of rotational solids like this is to think about them in terms of cylindrical shells. So I'll explain what I mean by that. So imagine that the region bounded by a function f and the x-axis over AB, or imagine the region bounded by a function f and the x-axis over AB that's been rotated about the y-axis. So let's say you've got this. Let's say that this is your function, right? Just kind of like a simple little curve. And you rotate this thing around the y-axis. So you're going to get a picture that looks something like this. Now, note that the cross-sections parallel to the y-axis are not washers. In other words, if you cut it this way, you're not going to get washers. You're going to get a really weird shape, something that's kind of like flat on bottom and like curved on top. But they're not going to be washers. However, the cross-sections parallel to the x-axis are washers, right? So if you cut this way, you'd get washers. But notice that you get washers, but you kind of would have to split right here. Like if you're trying to integrate this, first of all, you'd have to come up with an expression for the function in terms of y. So you'd have to solve for x and get something of the form x equals f of y, or g of y, I guess, in order to integrate. And then second of all, you'd have to split the thing right there. Because here the outer diameter would be b, the inner diameter would be a. Here the outer diameter would be g of y, and the inner diameter would be a. So you'd have to split it. Anyway, it would be kind of a little tricky. Not that you couldn't do it with the washer method, but it would be a little tricky to do with the washer method. And it requires you to be able to solve this thing, like I said, and get it like x equals g of y. That may not always be possible to do. Or it may be possible, but just really difficult to integrate once you do solve it. So we'd like another approach if possible. Having more than one tool in your toolkit is always a good thing, right? So here's another way to approach the problem. What we could do is calculate the area of the cylindrical sheet swept out by an arbitrary cross-section parallel to the axis of rotation. So in this case, the axis of rotation is the y-axis, right? If we take an arbitrary cross-section parallel to the y-axis, so like I'm thinking of like this kind of cross-section here, and then imagine just what happens to that line. Just imagine what happens to that straight line when it gets rotated around the y-axis. It turns into this cylinder, right? It turns into a cylinder that looks something like this. Now, when I say we could calculate the area of the cylinder, what I mean is that this is just a little tiny sheet, right? Like this cylinder is just a little tiny sheet. And if you imagine like cutting it along this line and then unfolding it, right? Unfolding it, what you would get is a rectangle. So you'd get this rectangle, and the height of the rectangle, well, that would be the function value, right? So the height of the rectangle is this thing right here. That's the function value. That's f of x. What about the width of the rectangle? Again, remember that you've taken the cylinder and kind of unscrolled it. So you've got this. So what is the top? What is the top part, right? What's the width of the rectangle? Well, that would be the circumference of the circle along the top here, right? And now what's that circumference? Well, the circumference in general is 2 pi times the radius of the circle. The radius of the circle in this case would be x, right? The radius of the circle would be x. So the circumference is 2 pi times x. Okay, so the area of this sheet, if you were to kind of unscroll it, the area of the sheet would be the circumference times the height, right? So that's 2 pi x times f of x. Okay, so that just gives you the area of one of these sheets. But now imagine that you found the area of this sheet, and this sheet, and this sheet, and this, and you found the area of all of the sheets between A and B, and then added them up. Well, then you would have the volume, of this solid, right? And so that's what we do, right? We integrate from A to B, 2 pi x f of x dx, right? And so this is called the shells method. We call these things cylindrical shells. And so we can calculate volumes by cylindrical shells. So let me give you an example. This one asks us to find the volume of the solid generated when the region enclosed between y equals x squared, or sorry, y equals square root of x equals 1, x equals 4, and the x-axis is revolved about the y-axis. So let's do that. Okay, so first of all, to draw a picture, so square root of x is going to look something like that. Right, this is 1, 4, this is 1 and 2. And then, we're going between 1 and 4. And we're rotating this thing about the y-axis. So we're going to rotate about the y-axis that way. Okay. The resulting solid is, I don't know why, but I have a hard time drawing these things. Maybe the resulting solid would, I guess, look something like this. So we'd have that, and we'd have that, and this thing is being rotated around the y-axis, right? So we have kind of like this. Well, I guess you wouldn't see that if you're rotating this around. So just imagine, right, that you're rotating this thing around, and you get kind of this sort of thing. This I guess would also come around in front like that. But anyway, so it's sort of like a funnel, right? It's sort of like a funnel, sort of like a funnel that would look, kind of like this, I guess, Yeah, there you go. That's a good picture of it. So this is what you'd get. Well, sort of, except that no, this is not. So it's actually the opposite, right? It's not the funnel part that you get. It's everything else. It's like, oh goodness. So I've botched this drawing, but it's like, well, just imagine it, right? It's this thing that you've swept out. So it's not the funnel. The funnel is sort of like the negative space. It's the stuff around the funnel. It's like the mold that you would use to make the funnel, I guess, if that makes sense. But anyway, so we can do this. We can finish this problem though. So, okay. Now, if you were to think like, how would I do this using the disc or washer method? Well, like we said when we were looking through this thing earlier, we said, well, you could do it by taking slices parallel to the x-axis, which means you'd have to integrate with respect to y. So, and in this case, since our function is y equals x squared, we can solve that for x pretty easily. We can say x is just y squared. So that's fine. So we could do this using the washer method. And what you'd do probably is you'd split it here. And you would just, like this part, you could find the area of those washers just using geometry, right? It would be pi times 4 squared minus pi times 1 squared times the height of that thing, which would be 1. So you can get the volume of that bottom kind of cylinder pretty easily. But then for this one, you do what? You would integrate from 1 to 2. You would want to do 4 minus y squared, I think. Anyway, so that's how you would do it using discs and washers. But let's do this using cylindrical shells. So using cylindrical shells, what we do is we take like an arbitrary sort of like cross section, right? So we take an arbitrary cross section, and now imagine that getting rotated around the y-axis. You end up with this cylinder, right? And if we call this thing x, then we can say, well, the radius of that cylinder is x, right? And the height of that cylinder is obviously f of x, or in other words, the square root of x. Or that's a poor way to write it, I guess. We would say it's the square root of x over here, right? So, okay, so then the volume is going to be the integral from 1 to 4 of the area of each of these little cylindrical shells that we get. The area of this cylindrical shell, like if you unfurl it, right, would be the height, which we said is square root of x, times the base, which we said would be the circumference of this circle, which would be 2 pi times the radius, and the radius is x, so it's 2 pi times x. Okay, and that'll do the trick. So the rest is history, right? I mean, this is like, okay, so this is 2 pi from 1 to 4. Square root of x is x to the 1/2, so x to the 1/2 times x is x to the 3/2. So that's 2 pi times x to the 5/2 divided by 5/2. So 2 2/5 x to the 5/2. You plug in 4, square root of 4 is 2, and 2 to the 5th is 32. 32 times 2 is 64, and 64 times 2 is 128. So I think we get 128 pi over 5. If we plug in 1, we get 2/5. 2/5 times 2 pi is going to be 4 pi. So 4 pi over 5. So we get 124 pi over 5. And that should do it for that one. Okay, so this is the idea behind cylindrical shells. It's actually pretty nice. And did I ever write down a formula? Yeah. I mean, so instead of having to think it through each and every time, you can just use this formula, right? You could say, well, it's 2 pi, but it's just integral from a to b of 2 pi x times f of x dx. So, so let's look at another one kind of like that. So this one says, find the volume of the solid generated when the region in the first quadrant between y equals x and y equals x squared is revolved about the y-axis. Okay. I might regret not working out this problem before I try to do it. Before I try to do it with you. Let's see. Let's see if we can scratch it out. So what are we talking about? We're talking about the area in the first quadrant. So the region in the first quadrant between y equals x squared and y equals x. Okay. So I happen to know that y equals x squared and y equals x both go through the point 0, 0, and they also both go through the point 1, 1. And y equals x does so in a straight path. Y equals x squared does so in a curvy path. So this is the little region that we're talking about. And it's being evolved. It's being revolved around the y-axis. So we're going to rotate it that way. I feel like we've done this volume before. Maybe we did it using discs and washers. But we're going to do it using cylindrical shells this time. Okay. Yeah, you could do this both ways, right? Using discs and washers, that wouldn't be too bad at all. And actually, this one isn't as hard. This one isn't as hard for me to draw as the previous one, because you would get well, maybe it's not. You would get this sort of thing, right? You would get kind of a bowl-looking thing like that. Well, anyway, so using cylindrical shells, imagine that you took just an arbitrary little slice here at x, and when you sweep that around the y-axis, you're going to get a cylindrical shell. Now imagine unfurling that cylindrical shell. What's the area? Well, the area is going to be the height, which in this case is not just f of x, it's actually going to have to be f of x minus g of x. It's going to have to be x minus x squared, right? That's going to be the height, is x minus x squared. So the volume is going to be the integral of, now the radius is still x though, right? So it's going to be the circumference of the top circle, 2 pi x, times the height, which is going to be x minus x squared, right? I get my hand in the way so then you can't see, but it's x minus x squared, okay? So x minus x squared dx. And of course we're going to do this from 0 to 1. Right? We're going to find the area of all of those cylinders between 0 and 1. And that should do it, right? That's not bad. Let's see what we get. So this is 2 pi times the integral from 0 to 1 of x squared minus x cubed, it looks like. I don't know why I'm doing that, because I can integrate these. This is x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 1. So 2 pi times, if I plug in 1, I get 1/3 minus 1/4. If I plug in 0, I get 0 minus 0. Boring. Okay, a third minus a fourth. A third is 4/12, and a fourth is 3/12. So that would be 1/12. So it's 2 pi times 1/12, which I think is pi over 6. Okay. And that's that one. Okay. So let me check in the book, make sure my answers are correct so far, because I don't want to lead you astray at all. What are we on? We're on 6.3. Pi over 6. Yep, so far so good. Okay, last one. One more example, and then we'll call it good. Because of course we can do cylindrical shells the other way around, right? Like if the thing's being rotated around the x-axis, we can still do cylindrical shells. Or even if we're rotating around a different axis altogether, like the line y equals -1. So let's take a look. It says find the volume of the solid generated when the region between y equals x squared and the x-axis over 0, 2 is revolved about the line y equals 1. Okay, so between y equals x squared and the x-axis over 0, 2. Okay, and we're revolving around the line y equals -1. Let's take a look. Zero, 2. So at 2, x squared is going to be 4, right? So I'm going to go 1, 2, 3, 4, 1, 2. Okay, so we've got y equals x squared. And it's between y equals x squared and the x-axis between 0 and 2. So it's this thing right here. And we want to revolve that around the line y equals -1. So this is going to be our axis of rotation. So we're going to go like that. This is y equals x squared. Okay. Okay. So again, we could do this with discs and washers, right? We definitely could do that. We would get but I think if you slice parallel to the y-axis with discs and washers, you would get a bunch of washers. But let's see if we can do this with cylindrical shells. Okay. So with cylindrical shells, so imagine now, since we're rotating around a horizontal line instead of a vertical line, we're going to take a horizontal slice instead of a vertical slice. So if I took an arbitrary horizontal slice like that, and I called it y, and then imagine rotating this around this line y equals 1. Now the question is, what is the radius of that cylinder, okay? And then what is the height of the cylinder? So the radius, now remember, since we're rotating around the line y equals -1, the radius is going to be, it's going to be y plus 1, right? So it's going to be y plus 1. So I'm thinking maybe if I just get like a formula for the area, then I can find the volume stuff in a second. So it's going to be, the area is going to be y plus 1 times 2 pi, right? So that's the circumference. That's the circumference of this cylindrical shell that we're going to get. And then we have to multiply that by the height of the cylinder. The height of the cylinder looks like it's going to be well, it would have to be x equals 2 minus x equals, so we're gonna have to solve this for x. So we get x equals square root of y, right? So it would be x equals 2 minus x equals square root of y. So it would be 2 minus square root of y. Okay. So there's the area of one shell. Obviously, we're going to integrate with respect to y. But that's for one shell. I'm going to do this for all of the shells between y equals 0 and y equals 4. So my volume is going to be the integral from 0 to 4 of 2 pi times y plus 1 times 2 minus square root of y dy. All right. So let's see if we can work this one out. So this is going to be 2 pi times the integral from 0 to 4. Here I would have to FOIL, right? So I get 2y minus y to the 3 halves plus 2 minus y to the 1/2, we'll say. That's not in descending order or anything, but it doesn't really matter. We don't have any like terms to combine. Let's go ahead and integrate. So this is 2 pi. This is going to be y squared minus y to the 5 halves divided by 5 halves, so 2/5 y to the 5 halves plus 2y minus y to the 3 halves divided by 3 halves, so 2/3 y to the 3 halves, evaluated from 0 to 4. So that's 2 pi times, if I plug in 4, I get 16 minus square root of 4 is 2. 2 to the 5th is 32, and 32 times 2 is 64. 2 times 4 is 8. And again, square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. And then minus, a bunch of zeros. Okay, 0 minus 0 plus 0 minus 0. Let's see if we can simplify this mess. You know what? I'm just going to use my calculator at this point. 16 minus 64 fifths plus 8 minus 16 thirds is 88 fifteenths. And then I'm going to multiply that by 2 pi. So that's 176 here. So I'll say this is times 88 fifteenths. And so that comes out to 176 pi over 15 as our final answer. Boy, I better check that answer. No, that's correct. That's what the book is saying. All right. So I guess you can get weird answers. Yeah, of course you can get weird answers. It happens. But that's that. So that's all I have to say about the cylindrical shell method. It's a nice method. I like it.